Hello, my name is Daniel Grimmer. I'm a DPhil student at the University of Oxford doing philosophy of physics. This is a job talk, or a practice job talk, which I prepared for a session which happened earlier today, but some people couldn't make it, so I'm recording another version for them. I am working in the metaphysics of space and time, particularly on some issues in spacetime non-fundamentality, which I'd be very happy to tell everybody about today. So the target of the talk is the spacetime manifold. So let's do a little bit of history first regarding this. So ever since Newton, our scientific theories have come along with an explicit spacetime background structure written into them. And for Newton, space and time were absolute. They were, in a sense, a fixed stage upon which the players of the world moved. As we move forward in time, though, to Einstein, space and time merge together, becoming the spacetime manifold. And moreover, they become an active dynamical player in the world's drama. Spacetime tells matter how to move, and matter tells spacetime how to curve. And I should point out at the start that you can understand the spacetime manifold in roughly two ways, either as a collection of spacetime points or as sort of a way of codifying the spacetime relations between things. So whether you're an absolutist or a relationalist about space, either one, I'm saying that there's still a spacetime manifold that exists in a lot of these theories from Newton to Einstein. But now as we move ahead farther to the present day, we see that our usual continuous 3+1 dimensional spacetime setting is under a new threat from quantum gravity. So the consensus in the quantum gravity literature, they don't have much consensus, but one thing which there's a widespread agreement on is that our usual notions of space and time have to somehow fail as we investigate smaller length scales and higher energies. Let me just briefly tell you how that's supposed to work. When we measure aircrafts, we measure their sizes and locations using radio waves. These are very long wavelength electromagnetic waves with very low energies. But in order to measure smaller things like atomic nuclei, we have to go to shorter wavelengths and higher energies, in particular X-rays. But to measure things at a very, very small scale down at the Planck scale, 10 to the minus 35 meters, would require such extremely high energies to be placed in such a small place that Einstein predicts that a black hole would then form and it would eat up whatever it is we were trying to study. So at least operationally, space and time have to lose their meaning at these sorts of scales. And this is a prediction out of quantum gravity. So how have physicists responded to this? We'll talk about how philosophers can respond in a second, but what physicists do is they are very eager to postulate new, unconfirmed physics that is in fact their job, but it's typically set on an exotic sort of space-time manifold. This is the flavor that a lot of the new theories have. Just to list out a few, string theory includes extra compactified dimensions. Supersymmetry includes fermionic dimensions. Causal set theory gets rid of the continuity of space and replaces it with a discrete spacetime with causal relations between discrete events. Loop quantum gravity says that there's a quantum spin foam. Roughly when you zoom in closer and closer to the world and look at it on smaller scales, things don't get smoother and smoother, but in fact they get foamy and quantum and strange in some way. Right. So many feel that in order to have a theory of quantum gravity, we're going to need a quantum space-time arena for things to happen in, that the arena itself has to become quantum in a way. And then our usual space-time manifold has to, of course, be recovered, and it's supposed to somehow emerge from this as we go to a certain energy scale or a certain regime or take some limit, something along those lines. But this issue of space-time emergence raises some difficult questions. There's a very big conceptual distinction between the space-time that features in our very well-established physics on the one hand, and these exotic space-time manifolds, or even a lack of space-time altogether, that features in these quantum gravity theories. So there's a really big jump between these two positions, and there's lots of details about how these connect to each other. And I don't have time to go into them now, but it's quite a issue for the philosopher and the physicist. So I've talked about what the physicist tends to do. They tend to be very forward-looking, and they tend to postulate new physics which they then might discover later on. They're very interested in discovery. Philosophers of physics, by contrast, can be more backwards looking in their approach, and they're more interested in understanding, or at least they can be, of like very clearly reinterpreting our old theories in light, and our folk theories in light of our current best physics. So there's a sort of reinterpretation of old physics, which the philosopher of physics can do, which the physicist typically doesn't. Let me give an example of this, which will be motivating for what's to come later. We can reinterpret Newtonian theory, Newtonian gravitational theory, in light of the discoveries which Einstein has made. And like we have this big conceptual jump before, there's a similar conceptual jump between these theories. We have this fixed, flat space-time in Newtonian gravity, and a big jump away from this seems to be the curved space-time that exists in Einstein's gravity. So how can we cross this big conceptual divide? Like I just said, there seems to be a very large jump between Newton and Einstein, but it turns out that you can rewrite Newton's theory in terms of what's called Newton-Cartan theory to make exactly the same predictions. So predictively and empirically, it's still Newton's theory, but you rewrite it so that it's on a curved spacetime. So now we have this Newtonian theory on a curved spacetime, just like Einstein's theory is on a curved spacetime, and then you can compare them at this level, and it turns out that it's a much smaller jump between these two theories at that point. So by writing Newton's theory in a form which is as close to Einstein's theory as possible, the gap between them shrinks considerably. So, suppose that Newton had anticipated the need for a curved spacetime. He didn't, and he probably has lots of philosophical reasons for thinking that's something he shouldn't do. But moreover, he didn't have the necessary mathematical or conceptual tools. If he did have those tools, then he could have already rewritten his theory in terms of a curved spacetime. And my claim is that this would have made Einstein's theory then easier to discover if he'd gone ahead and reinterpreted his old physics in light of what he anticipated coming. So we're in a similar position, I'm saying. So in light of quantum gravity, we anticipate that at least certain aspects, we're not quite sure which ones, or maybe the entirety of our usual space-time settings are supposed to be emergent somehow out of quantum gravity, and hence they're not going to be fundamental. There's some non-spatiotemporal things which somehow the space-time emerges out of. Something like this. We're not exactly sure how the story goes. But if we have the necessary mathematical and conceptual tools, which it's not sure that we do, then we could already go ahead and start to rework our well-established physical theories with space-time non-fundamentality in mind. So just like Newton could rewrite his theory on a curved space-time, we can go ahead and already build in space-time non-fundamentality into our old theories. And the hope is that this will then make a quantum gravity theory easier to discover. Now the main difference is that in that Newtonian case, we sort of assumed we knew where he was going towards this Einsteinian theory, whereas in quantum gravity we're a little bit lost. But if we believe this space-time non-fundamentality or this emergence is going to be a part of our quantum gravity theories, we can go ahead and try and work those in. And so all of this is dependent though on us having the right mathematical and conceptual tools, and this is where I then come into the story. What I'm doing with my PhD here in Oxford is to build these sorts of mathematical and conceptual tools to help us reinterpret even our very old theories with space-time non-fundamentality in mind. Roughly, my strategy is as follows. We're going to see the space-time as a sort of representational artifact. That is, we're going to get space-time non-fundamentality through a notion of space-time redescribability. And people have seen hints of this sort of thing at the forefront of physics with the ADS-CFT correspondence, which I'll just briefly overview now. The technical details of it are not important, it's just sort of the spirit of it which I'd like to communicate. So, physicists have found that there's certain gravitational situations in anti-de Sitter space, which exist in 3 spatial dimensions, in the bulk, they say, but this has an equivalent description in terms of quantum effects which happen on the boundary of this space-time. So a 2-dimensional surface on the boundary. And these are in 1-to-1 correspondence with each other, in a sense. So they make all the same predictions, and you can find for every observable of this theory, you find an equivalent observable of this theory. So you can really describe things in either way. The very same physics then can be described on two very different topological manifolds. Now, there's lots of ways to interpret this, but some physicists and philosophers believe that this suggests that these are just two representations of some fundamentally non-spatiotemporal physics. Now, it's unclear what that common core is exactly, but we have hints about it maybe. But this is just the general spirit of the program. And to help even more, an analogy which might aid in our thinking here is coordinate systems. So the world doesn't exist with coordinates on it. These are things we impose on the world to help us in theorizing about it. We lay out a Cartesian coordinate system or a spherical coordinate system, whichever coordinate system we like. It's nothing metaphysically substantial about the world. When we see these appearing in our theory, we ought to understand them as just representational artifacts to do with how we're representing our physics. Right? And it's our ability to change between different coordinates and see them as describing the same thing in some way that allows us to say that they are just representational. So, I've built a tool which works along these lines. It's called the ISE methodology, and I'll tell you what those initials mean in a moment. But it allows us to make these sorts of space-time descriptions, sort of like the ADS-CFT thing, although I'll give you some more examples in a moment. It allows us to make those sorts of redescriptions very generally. You give me almost any physical theory set on a space-time manifold. There's certain conditions that have to apply, but it's very general. And then I can redescribe it for you as being set on really a wide variety of different space-time settings. So, given all of these space-time settings, the ultimate claim I want to drive at is that the space-time manifold isn't anything metaphysically substantial. It's not really doing any heavy metaphysical work, but rather it's just merely one nice way, among others, of codifying the dynamical behavior of matter. And at the end of the presentation, I'm going to connect this with some views from David Lewis and from Immanuel Kant and from really quite a lot of people. But let me just get the view out there clearly, and then we'll make some connections. So how does this ISE methodology work? It works, it's a three-step process with one step for each letter in the initialism. So we have internalize as the first step. So you give me a space-time theory mathematically, then I will sort of conceptually divorce the dynamical behavior of matter from any assumed space-time background structure. And there's a well-developed technique for doing this in the philosophy literature already. It's called the algebraic approach to space-time. And there's a way of thinking about the physical fields described by our theories as existing without any underlying manifold. So there's this sort of divorce that you can mediate. But after this, I sort of stray away from what's typically been done in the space-time algebraicist program. The second step in the ISE methodology is to search for a new space-time setting. In particular, we're going to search for the building blocks out of which we can construct a new space-time representation of our theory. And these are what I call pre-space-time translation operations. That's PSTOs. Once you have these building blocks identified, you use them, and use these hand-picked pre-space-time translation operations. You're free to pick them as you like to construct a new space-time setting for the theory in question. And by construction, the chosen PSTOs will end up being honest-to-goodness space-time translations in the new theory. Roughly what we do is we find these objects which are like space-time translations in some analogous sense, and then we just take that analogy very seriously and build a new space-time in which those are literally space-time translations. Let me say a little bit more about what these pre-space-time translation operations are. They are a certain kind of smooth transformation on the theory's states. So a theory comes along with a catalog of all the possible states of the world, and this is a way of smoothly transforming them into each other. A little more technically, it's a Lie group action with certain properties which, when judged by how they act on the theory's states and judged on nothing else, they sort of have the same mathematical characteristic as space-time translations. So these are things which are mathematically passable as space-time translations. I'm going to give you 3 examples of these, and then we'll start making some philosophical connections. So here's a trivial example of pre-space-time translation operations. The old theory's rigid translations in space-time, they count as PSTOs, right? And so here's an image of this on the left. We can shift this state around back and forward to the left and to the right. Any of these are valid translations of the other one, and you can imagine them smoothly moving between each other. So we have this smooth way of deforming the state, and mathematically that's written here. We have a wave function or a field in space and time, and then this evolves forward, or it's shifted by a units to the left or to the right here. And if you take these and put them into the ISE methodology, you externalize them, and it gives you back the theory's old space-time setting. So we can always go back to the old space-time setting. But the point is that there's other options for us as well. So here's our first non-trivial example of pre-space-time translation operations. Consider a sort of wave theory that's talking about waves in some fundamental field. What you can do, just like you could smoothly translate the wave around, you could also smoothly increase the frequency of all of the waves. So here's a little image of this. We have this wave with this well-defined frequency, and then we can increase the frequency, and you can imagine this being done smoothly. And then you can smoothly decrease the frequency of this wave and all waves. Just like you might shift everything around, you might also pitch everything up or down. And don't worry too much about the mathematics. The pictures are all sufficient to get the idea across. So these changes in frequency, they are rigid translations actually, not in space-time, but in Fourier space. So here you multiply by this exponential, this wave factor here, but this is just to translate in Fourier space. The tilde here indicates the Fourier transform. And then we build a new theory where these translations in Fourier space are honest-to-goodness translations in the new theory space-time. So what were rigid translations in the Fourier space of the old theory, after externalization, they become, we construct the new space-time such that they are honest-to-goodness space-time translations in the new theory. And so the ultimate result of this is that the new theory's space-time is the old theory's Fourier space. And then you could, of course, go back. So you can take the Fourier transform and switch back and forth between these different representations of the theory. So I'd like to give one more example of pre-space-time translation operations to show just the variety which can exist, and then we'll talk about some philosophical connections. So I'm very much inspired by this paper from Achim Kempf at the University of Waterloo, who says that space-time could be simultaneously continuous and discrete in the same way that information can be. But how is this possible? How can you redescribe things in a way which is both either continuous or discrete? Remember from earlier, we had this ADS-CFT correspondence where we described something in 3 dimensions and then also in 2 dimensions. So these sorts of changes in dimensionality are possible. You can also change from continuous to discrete and vice versa. So I did that in these papers here, 3 and 4. Shows how you can use this ISE methodology to switch between a discrete and continuous framing of a theory. Let me just show you what these look like as pre-space-time translation operations here in this figure on the left. So theories that are set on a discrete space-time, like on a lattice here. So this is a lattice in space, and we have the field value defined at all these different points. You can obviously do discrete translation operations to these. So here it's moving to the right, and I move it back to the left, back to the right, and you can move these things around discretely. It turns out, though, that there's also a certain way of smoothly changing the states into one another, such that you get what qualify as pre-space-time translation operations. Now, let me show you what those look like. So we could move things around discretely, like here. But we could also shift things around in a continuous way. Everything deforms here a little bit locally around the point that's moving, and then it's shifted over once. Let me show you this again. So imagine these being smoothly connected, smoothly, and then we get the discrete shift. So there's this smooth way of implementing these discrete shifts, which when you look at that smooth transformation mathematically, it looks just like a space-time translation, right? In the same way that the Fourier transformations look just like space-time translations from a certain perspective. So using these continuous pre-space-time translation operations, if you take them seriously as space-time translations, you end up building a new continuous space-time description of the theory. And let me just show you roughly how that would work in practice. So here we have a discrete heat equation, which I'm going to re-describe in a continuous way. So here's some heat associated with different lattice-sites, so these are different temperatures. And then you can evolve those temperatures forward in time. The hot things get colder, the cold things get hotter, the temperature sort of smooths out. It's a very common physics equation to solve the heat equation. So here we have this discrete heat equation. Right? Now, using that continuous pre-space-time translation operations I just discussed, you can build a continuous representation of this theory, and here I presented it. So this initial state, which used to be discrete, we now have a continuous description of it. And we also have a continuous description of the time-evolved state. And so we also carry the dynamics across. So in terms of the states and the dynamics, we have a one-to-one correspondence between this discrete description and the continuous description. And it's all mediated via this ISE methodology I've been talking about. So it's not that the discrete system is an approximation of the continuous one. They are in an exact one-to-one correspondence. They are just re-descriptions of exactly the same sort of algebraic content of the theory. So now let's connect this with some philosophy that you may have heard of. Given all of these possible space-time descriptions, what makes the one we're familiar with, the intuitive one, what makes that one jump out as something special that we should care about? There are three analogous views that I feel are worth discussing. First, we have David Lewis on his view of the metaphysics of laws. He argues against the world's primordial nomological structure. So he's here worried about the laws of nature. He says, to paraphrase, the laws of nature are nothing metaphysically substantial. They don't govern the world or have any sort of active force on the law. Rather, they're just one nice way, among others, of codifying the dynamical behavior of matter. And in fact, he thinks they're objective and mind independent, in the same way that, suppose I showed you many games of chess. Every possible game of chess I showed them to you, you could well enough look at all those patterns and figure out what the rules of chess are from them. In the same way, you could sort of objectively look at the world and find out what the laws are. The way Lewis says to do this is by taking the laws to be the axioms of whichever logical system describes the world with the best balance of simplicity and strength. And he thinks there'll be a far and away clear winner of this, such that the laws are there objectively and mind independently, as the sort of most economical description of what's going on. You might say the same thing about the space-time manifold, on my view. We have all these different possibilities, and then you judge them via some contest about which gives the simplest and strongest description of the world. Here's a second view to connect with. We have the dynamics first approach to geometry, which is put forward by Harvey Brown and Nick Huggett, among many others. But they argue against the world having a sort of primordial geometric structure. Whereas again, I'm worried about the topological structure. They say that the pieces of geometric structures which appear in our theories, so when you write down a physics theory, some beats of geometry sort of pop out, but we shouldn't take these to be anything metaphysically substantial. Rather, they earn their sort of chronogeometric significance, their ability to count out distances and times, via the relationship to the dynamics of measuring rods and measuring clocks. So it's not that there's distances and times primordially there in the world and our measuring rods happen to latch onto them. It's that we take a dynamics first approach to geometry, so that we have to look at the dynamics of rods and clocks first. And geometric structure comes out of this. And the third view I'd like to speculatively connect with here. I'm no Kant scholar, but I think there's some connection here possibly with Kant's transcendental idealism. So here's a quote from Kant. Space is not something objective and real, so we're disagreeing with Lewis here, nor a substance, nor an accident, nor a relation. Instead, it is subjective and ideal, and originates from the mind's nature in accordance with a stable law as a scheme, as it were, for coordinating everything sensed externally. So here we get this sense that Kant is saying that the mind projects space and time onto the world, in a sense. So space is not a part of the mind-independent world, but rather it's an a priori intuition which we have, which is baked into our cognition and into how we represent the world. I do find some sympathies with this Kantian view in my work, and I'd really like to develop them further. If there's any Kant scholars who would like to collaborate on this, I'd be more than happy to talk. So, in conclusion, in order to help us discover the next theory of quantum gravity, in order to make it a smaller jump, as I talked about with Newton-Cartan theory, we're motivated to go ahead and already reinterpret our well-established physics from a perspective of space-time non-fundamentality. So we don't have to do this by studying theories of quantum gravity. We take the lessons we think we'll learn there and go ahead and apply them at home to our well-established theories. So to this end, I've developed this ISE methodology, and it's a powerful tool for investigating and negotiating between a wide range of different space-time settings for a given space-time theory. It's a lot like switching between coordinate systems in this way. And given all of these alternate space-time descriptions, I claim that the space-time manifold is nothing metaphysically substantial, but rather it's just one nice way, among others, of codifying the dynamical behavior of matter. And that could be in a sort of realist way along the lines of Lewis, or it could be more in an idealist way in lines of Kant. I'm sort of open on this point. So here are some references, and thank you for your attention.